we're going to start in chapter 8 by looking at certain topics such as electron configurations and how it's related to the positions of the elements in the periodic table. And what you're going to see in this chapter is that it's a natural follow-on from what we discussed in chapter 7, where we were introduced to the whole concept of orbitals and the energy levels and sublevels and all that good stuff. Okay, so first thing I'm going to talk about is comparing what we call the orbital energy diagrams between the hydrogen atom, which of course has only one electron, and a typical multi-electron atom. So pretty much any other atom from helium onwards, all right? So if you compare the energy diagram here for hydrogen for a typical multi-electron atom, you're going to notice two things, right? The first of which is that basically all the energy levels that you see here in the case of the hydrogen atoms will be lower in the case of the multi-electron atom, right? So for example, the first energy level, which contains the 1s orbital, is here. In the case of the one electron atom, like hydrogen, down here, it will be lower, all right? The same is true for the second shell, which contains the 2s 2p set of orbitals. It's higher here compared to what happens in the case of the multi-electron atom, and so on and so forth. So that's the first thing you'll notice. The second thing you'll notice is, as stated in this box right here, is that when you get to shells that has more than one type of orbital, such as the second, third, and fourth, and so on, what you'll find is that all these orbitals will have the same energy in those shells, right? So for example, the 2s orbital will have the same energy as the orbitals in the 2p sublevel. Same thing here in the third shell, where the 3s orbital will have the same energy level as the 3p orbitals, which in turn will have the same energy level as the 3d orbitals. And the same is true for the fourth shell, fifth shell, and so on. That is not true when you move on to the typical multi-electron atom, because what you're going to see is that there's going to be a breakdown in terms of the energy levels being equal to each other for the different subshells. So for example, here we have the n equal to subshell, but within this subshell, the 2s orbitals would be lower in energy compared to the 2p orbitals. And the same thing is observed when it comes to the third shell and the fourth shell and beyond, all right? So as a result, things are not as orderly when it comes to the arrangement of the orbitals in terms of their energy when it comes to a multi-electron atom, all right? Okay, what else shall we say here? Oh, I mentioned this point already. Orbital energies are lower in the multi-electron atom compared to in the case of the hydrogen atom. That's the first thing I mentioned on this slide. All right, so this brings us now to talking about what is called the electron configuration, which is basically a description of how the electrons are distributed among the orbitals in an atom. And there are two main ways that we can represent the electron configuration of an atom. We can use what is called this SPDF notation, which uses numbers to designate the principal shell, letters to designate the type of subshell, and then a superscript number which indicates the number of electrons in the subshell. So you will see something like this when you're using that type of notation. So in this particular case, what this one represents is the energy shell or the energy level. This represents the type of subshell within that energy level, and this number here, the 2, represents the number of electrons present within that subshell, all right? So that's basically what the SPDF notation is all about. So that's one way of expressing or representing the electron configuration of an atom. Another way, which is actually more explicit and gives more information, is what is called the orbital box diagram, right? And an example is shown here. And you'll notice that in this example, and this is for the element nitrogen, for that nitrogen atom, we use boxes to represent the orbitals, and we use arrows to represent the electrons. And you'll notice that the arrows are pointing up and down in this representation, because as you're going to see shortly, the direction of the arrows is basically representing what we call the spins. In fact, we talked about the spins of electrons at the end of chapter 7, because remember we said that the spin of electrons are quantized and they can spin in one of two directions, clockwise or counterclockwise, which correspond to two quantum numbers, ms equal plus half and ms equal minus half. So that's basically what this represents here. So the typical convention that is used when it comes to the arrow spinning in different directions or pointing in different directions is that the arrow pointing up represents the electron with the spin quantum number of plus half, and the arrow pointing down represents the spin quantum number of minus half, right? And a couple of things I want to point out here. You'll notice that electrons occupying the same orbital will be spinning in opposite directions, right? And we're going to talk about that in more detail shortly. Another thing you'll notice is that all the electrons occupying the 2p sublevel, right? Well, for one, they're occupying each p orbital singly, and they're spinning in the same direction, all right? Okay, so that's the orbital box diagram. As I said before, this gives more information because it tells you explicitly, especially where you have a sublevel containing more than one orbital, such as the 2p sublevel. It shows you explicitly where the electrons are located. So, and in this case here, it shows you that each orbital of the 2p sublevel is occupied by a single electron. If you're given the SPDF notation for this, let me just do that here just to show you what that looks like so you can compare. The SPDF notation for the nitrogen atom would be, okay, this thing is not working. Let me try this quickly. Okay, let's see. Okay, now it's working. So it's 1s2, 2s2, 2p3. So this is the SPDF notation, and this is the orbital diagram representation. And the point I was making about this being more explicit is that in the SPDF notation, all it tells you here is that the 2p sublevel contains 3 electrons. It doesn't tell you how the electrons are distributed. In the case of the orbital diagram notation, it shows you that in the 2p sublevel, each orbital is occupied by a single electron. Okay, so what shall we talk about next? Okay, so let's get into the rules for determining the electron configuration. And in this case, the rules that I'm about to describe is specifically for atoms in, excuse me, in the ground state configuration. If you remember, we said in chapter 7, the ground state configuration is a configuration that has the lowest energy state and therefore is the most stable configuration. All right. So the first rule for determining the electron configuration of an atom is that electrons will ordinarily occupy the orbitals of lowest energy available. All right. So basically, the electrons will simply try to be placed into the lowest energy orbital in the ground state. And then we get to the explanation as to why the electrons occupying the same orbital will be spinning in opposite directions. This is actually stated by Pauli exclusion principle, which says that one atomic orbital can accommodate no more than 2 electrons. And these electrons must have opposing spins. All right, so that's Pauli's exclusion principle. So therefore, basically what this principle says is that if you have 2 electrons occupying the same orbital, then those 2 electrons must be spinning in opposite directions. You cannot simply have 2 electrons occupying the same orbital and spinning in the same direction. All right. Okay, the next rule, another way of stating Pauli's exclusion principle is that no 2 electrons in the same atom may have all the same set of 4 quantum numbers. All right, so basically what that is saying is that when you look at the N value, the L value, the ML value, and the MS value, if you take any 2 electrons in the same atom, you cannot find a situation where those 2 electrons will have the same N value, L value, ML value, or MS value, even if the electrons are occupying the same orbital. So if you have 2 electrons occupying, let's say, the 1s orbital, they will have the same N value, they will have the same L value, they will have the same ML value, but what they will not have is the same MS value, because if they're occupying the same orbital, they must be spinning in opposite directions. So therefore, the MS value for one electron will be plus half, and the MS value for the other electron will be minus half. All right. The next rule has to do with how to distribute the electrons in a group of orbitals that have the same energy. And basically what this rule says, and this is Hund's rule, by the way, it says that electrons will enter the empty orbitals whenever possible. All right, so that goes back to what I was talking about. In fact, let me get out of this here so as to explain this further. I'm just going to insert a slide here. Let me choose this one. Okay, so let me do this, and then let me go here, here. Okay, so in this particular, the nitrogen, remember we talked about nitrogen. I'm just going to recreate the orbital diagram for nitrogen. All right, and then we have the p orbitals here. All right, so basically for nitrogen, the atomic number is 7. The first 4 would go into the 1s orbital. Let me erase this here. The first 4 would go into the 1s orbital and the, and the 2s orbital, right? So the next 3 electrons, it becomes a question as to where the electrons will go. So basically the 5th electron will go into the into one of the empty or vacant p orbitals, 2 p orbitals, and then the next electron will go into the other vacant p orbital, and then the so that will be the 6th electron. Then the 7th electron will go into the remaining vacant p orbitals. So basically, what Hund's rule is saying is that when you get to a situation where you have to distribute the electrons among a set of orbitals of equal energy, you assign them to each orbital singly first. All right. Now, for the next element, which is oxygen, which has 8 electrons, the electron configuration will be what I'm about to draw here. All right. So I'm starting off with the nitrogen electron configuration. So this would be accounting for the 7 electrons added, right? And then the 8th electron, because remember now the atomic number is 8, the 8th electron is free to enter any one of these 2p orbitals. Remember, this is 1s, this is 2s, and this is 2p. So therefore, we can simply put the 8th electron into one of the p orbitals, which is already occupied by the electron. But of course, according to Pauli's exclusion principle, that electron that is added must be spinning in the opposite direction to the electron that was there before. All right? Okay, so that is basically Hund's rule. So let me go back to the rules again. So we were discussing Hund's rule, and then the next rule, which is actually an extension of Hund's rule, or part of Hund's rule, electrons in half-filled orbitals must have parallel spins, right? And to illustrate that, let me go back to this again, because you'll notice the way this is done. All these electrons that are occupying the 2p sublevel, remember now each orbital is occupied by a single electron. These electrons must be spinning in the same direction for the ground state configuration. So that's basically what that rule is talking about, all right? Okay, so that's basically the rules. Now the next thing I want to talk about is, you know what? Let me stop this video here. I'm going to stop this video here. And then the next video, I will get into the order of the subshell energies. Okay, until next time.